So in Module 18 and 19, we were talking about visual senses, and in Module 20, we're going to talk about audition or hearing. So by the end of this unit, if we do our jobs right, you should be able to describe the process by which audition occurs, the theories that help us understand pitch perception, and how we locate sounds. So sounds play a really important role in our mood, actually, and I don't know if you're even paying attention to the background music that's going on right now, but I purposely chose it because it can affect your mood. So this type of music isn't necessarily utilized to help you learn the best, so I'm going to turn it off shortly, but pitches and different types of music in your audition can set a tone for your own expectations and even affect your own physiological being, the way that you're feeling and your ability to receive information. So like our other senses, our audition or hearing is really highly adaptive. We hear a wide range of sounds, but the ones we hear best are those sounds with frequencies in a range corresponding to that of a human voice. So those with normal hearing are acutely sensitive to faint sounds, an obvious boon for our ancestors' survival when hunting and being hunted, or for detecting a child's whimper. If our ears were much more sensitive, we would hear a constant hiss from the movement of air molecules. We're also remarkably attuned to variations in sounds. We can easily detect differences among thousands of possible human voices. Walking between classes, we immediately recognize the voice of a friend behind us. A fraction of a second after a spoken word stimulates the ear's receptors, millions of little neurons have simultaneously coordinated in extracting the essential features, comparing them with past experiences, and identifying the stimulus. But not everybody has this ability. So audition is the sensor active hearing and in this section we're going to talk about the stimulus input, sound waves. So draw a bow across a violin and you'll unleash the energy of sound waves, jostling molecules of air, each bumping into the next, creating waves of compressed and expanded air like the ripples on a pond circling out from a tossed stone. As we swim in our ocean of moving air molecules, our ears detect these brief air pressure changes. Like light waves, sound waves vary in shape. The amplitude of sound waves determines their loudness. So amplitude determines their loudness. Their length or frequency determines the pitch we experience. So the number of complete wavelengths that pass a point in a given time, the frequency, determines the pitch of the sound that we hear. Long waves have low frequency and a low pitch. Short waves have a really high frequency and a high pitch. Sound waves produced by a violin are much shorter and faster than those produced by a cello or a bass guitar. We measure sound in decibels, with 0 decibels representing the absolute threshold for hearing. Every 10 decibels corresponds to a tenfold increase in the sound's intensity. So a normal conversation comes in at about 60 decibels, and it's 10,000 times more intense than a whisper, which is about a 20 decibel, reading. A temporarily tolerable 100 decibel passing subway train is 10 billion times more intense than the faintest detectable sound by the average ear. The intricate process that transforms vibrating air into nerve impulses, which our brain decodes as sounds, begins with sound waves entering the outer ear. There's a mechanical chain reaction that begins as the visible outer ear channels the waves through the auditory canal to the eardrum. The eardrum is a tight membrane, and the sound waves cause that to vibrate. In the middle ear, so there's three parts to the ear. The outer ear is the part that we've been talking about so far, but then right about here you hit the middle ear. In the middle ear, three tiny bones. They're nicknamed the hammer, the anvil, and the stirrup. I'll show you the formal terms for them in just a second. If you're in sports medicine, you might already know those formal terms. Those pick up the vibration and transmit them to the cochlea, which is part of the inner ear. So here, this is the inner ear here. The incoming vibrations cause the cochlea's membrane, which is called the oval window, to vibrate, and that jostles the cochlea, that snail-like shape here. It's filled with liquid. And the oval window's jostling vibrates the fluid inside of that tube. The motion causes ripples in the membrane, bending. There's little hair cells inside lining the surface, and so the water moves these hair cells that are along the surface. And the hair cells' movements trigger impulses in the adjacent nerve cells. Axons of those cells converge to form an auditory pulse, which sends messages up to the thalamus, to the auditory cortex in the brain's temporal lobe, from vibrating air to fluid waves and electrical impulses in the brain, while we actually hear sound. So you've been doing that whole process this whole time that we've been listening to this, because you're hearing sounds in the background and you're hearing me, obviously, as well. Here again is the outer ear, the middle ear, and the inner ear. And I'm going to stop right here and show you a like 2.5 minute, more formalized version of this. For each of the lessons, I've also put up the Khan Academy equivalent in case these help more than your regular lessons. They're not required, but they might help you to understand things more thoroughly. So look for them in Google Classroom.
Imagine that I clap my hands. Now sound waves are going to travel through the air and they're going to go towards your head. And the very first thing that they hit will be this outer visible part of the ear. So this is when you look at someone's ear, this is what you see. And this outer visible part of the ear is something known as the pinna. Something known as the pinna. So these sound waves get funneled by the pinna down into this smaller structure known as an auditory canal. And this is also known as a external auditory meatus. So I'll write that down here. So external auditory meatus. So these sound waves travel down the external auditory meatus, and the next thing that they hit is the eardrum, or tympanic membrane. So the next thing that they hit is the eardrum. Now, what the eardrum does is it actually starts to vibrate. So as this pressurized sound wave hits the eardrum starts vibrating back and forth. And when it's vibrating back and forth, it actually causes these little bones. So there are 3 little bones here. 1, 2, and 3. And it causes these 3 little bones to vibrate. The first bone is known as the malleus. The second bone is known as the incus. And the third little bone over here is known as the stapes. So let's just recap real quick. So the sound waves come in, get funneled by the pinna into the external auditory meatus, otherwise known as the auditory canal, then hit the eardrum, otherwise known as the tympanic membrane, and the eardrum starts to vibrate back and forth. And this vibration causes 3 little bones known as the malleus, incus, and stapes to vibrate back and forth.
Also known as the hammer, anvil, and stirrup.
Accordingly. So the next thing that happens is the stapes is attached to this oval window over here. So it's known as the elliptical window, which I'm underlining here. It's also known as the oval window. So this oval window starts to vibrate back and forth as well. So the next thing that happens is there's actually fluid. So this structure that the oval window is attached to is known as the cochlea. So this round structure right here is known as the cochlea. So inside the cochlea is a bunch of fluid. And as the oval window gets pushed inside and outside of the cochlea by the stapes, it actually pushes the fluid. So it causes the fluid to be pushed this way and causes the fluid to go all the way around the cochlea, and then it keeps going all the way around the cochlea until it reaches the tip of the cochlea. And when it reaches the tip of the cochlea, what does it do? Well, the only thing it can do is go back. And so now the fluid's going to have to go back. So we'll just follow this green line over here. So the fluid moves back towards where it came, but it actually doesn't go back to the oval window. It actually goes to this other window known as the circular or round window. Oops. Fix that so it goes to this circular or round window. And it causes the round window to get pushed out. So this basically keeps happening. So the fluid moves all the way to the tip of the cochlea, all the way back out, and back and forth, until the energy of this sound wave actually causes eventually the fluid stops moving. All that energy is dissipated. And meanwhile, hair cells inside the cochlea are being pushed back and forth, and that transmits an electrical impulse via this auditory nerve to the brain.
Okay, and then from that point, of course, the neural impulses travel to your auditory cortex, which is part of your temporal lobe, and sound is interpreted by your brain. Interpreting being the key word. Okay, so of course it doesn't work this way for everybody, so we're going to talk really quickly about hearing loss. So damage to the cochlea hair cell receptors that were mentioned earlier, or their associated nerves, can cause hearing loss or nerve deafness. So damage to the cochlea hairs is one of the ways in which you can experience hearing loss, but there's a less common form of hearing loss. It's called conduction hearing loss, and it's caused by the damage to the mechanical system that conducts sound waves to the cochlea itself. If you experience that kind of hearing loss, you can have cochlea transplants, which you might have a family member that has cochlear transplants. Occasionally, disease can cause hearing loss, but more often the culprits are biological changes linked with heredity, aging, and prolonged exposure to noise of some sort or really loud music. The cochlear implants is a device for converting sounds into electrical signals and stimulating the auditory nerve through electrodes that can be transplanted into the ear canal. Before we leave hearing loss behind, hearing loss is actually on the rise amongst teens. Here's a little bit about that. So the rate of teen hearing loss is now 1 in 5. It has risen by 1/3 since the early 1990s. Teen boys are more likely than teen girls or adults to blast themselves with really loud volumes of music for long periods of time. And if you look back at the 1990s and that growth of hearing loss, it's associated with headphones and earbuds and things like that. Males' greater exposure to noise may help explain why men's hearing tends to be less acute than women's as they age. But male or female, those who spend many hours in a loud nightclub or behind a power mower or using a jackhammer, you should really wear earplugs. For now, the only way to restore hearing for people with nerve deafness is the bionic ear, a cochlear implant. By 2009, they had been given to as many as 188,000 people worldwide, and those numbers continue to grow. Place theory presumes that we hear different pitches because different sound waves trigger activity at different places along the cochlea's basilar membrane. Thus, the brain determines a sound's pitch by recognizing the specific place, thus place theory, on the membrane that is generating the neural signal. When Nobel laureate Gog Ben-Beksky cut holes in the cochleas of guinea pigs and human cadavers and looked inside with a microscope, he discovered that the cochlea vibrated rather like a shaken bedsheet in response to sound. High frequencies produced large vibrations near the beginning of the cochlea's membrane. Low frequencies vibrated more of the membrane, including near the end. But the problem remains, place theory can't explain how we hear high-pitched sounds but not low-pitched sounds. Frequency theory suggests an alternative, that the brain reads pitch by monitoring the frequency of neural impulses. And we're going to leave it right there.